Today's presentation is about K2, a mobile operating system for heterogeneous coherence domains. So through this research paper, we are going to give a brief introduction about uh, the K2 prototype operating system and how we are going to, what is the overview of K2 operating system, K2 hardware platform, and what are the core services of K2 operating system. Before going to that K2 operating system, I would like to draw your attention why these people come with this K2 prototype operating system. For example, nowadays, the reason is nowadays we have come up with this variety of embedded applications. For example, mobile multimedia gadgets, high-end cell phones, wireless network applications. So these applications include more comprehensive functionalities, higher performance demand, and new uh, low power consumption. So these requirements proves that having a traditional single processor based systems no longer appropriate for realization of such applications. So this application demand forces us to give the birth to this system on chips. So in here we are going to discuss what is this system on chips and how uh, this mobile system on especially mobile system on chips. So in here the mobile system on chips that incorporate heterogeneous coherence domains will promise high energy efficiency to a wide range of mobile applications. So uh, in here we have come up with this heterogeneous and coherence. So what does this heterogeneous and coherence means? Heterogeneous means a different kind, using more than one different kind. So in here heterogeneity of modern computing systems gradually rises in chip area, and scaling of technologies allows for formally discrete components to become integrated part of a system on chip. So the heterogeneity of system increase the complexity of the hardware-software partitioning problem, and also the programmers will find that heterogeneous SoCs is another challenge to challenge when when they come to the programming. And also in here we are using heterogeneous cores. So in system on chips has multiple types of different cores that provide different performance power trade-offs. These cores will have different instruction set architectures. So this heterogeneity means we are using more than one different kind of cores. And then the next word we have come up with is the coherence. So what does this coherence means? Coherence in system on chip introduces the complexity and overhead. It may be regarding the caches, state bits, invalidations in exchange for a clean and uniform shared memory model. So this shared memory services are quite often needed crucial property of these such systems, therefore providing coherent weave, ensuring memory consistency and still achieving the desired performance is another challenge we are going to come up in this research paper. And then so let's move to the, for example, now we talk about the heterogeneous coherence domains. So these ARM holdings, they have come up with this ARM Big Little architecture. So this architecture is a heterogeneous computing architecture that this is developed by the ARM holdings. So we can see that this hardware heterogeneity is already embraced nowadays. So for example, this ARM Big Little is one of the many power management technologies employed by this ARM holdings to save the power in mobile system on chips. So this architecture has cores of different strengths in one cache coherence domains. So in here, in this architecture, we have different cores and these different strengths in one cache coherence domains. So this coherence allows a processor to move from big and little cores at the cost close to the context switch. So in here they have purposefully used this strong and weak domain respectively, uh, because to distinguish them from heterogeneous cores in the same domain that are already known as big and little. And also the absence of the hardware coherence allows cores in the weak domain to be orders of magnitude weaker and lower power than those in the strong domains, providing much better energy efficiency for light tasks than the big little architecture. So then the problem is when we are working with these, now we know this hardware heterogeneity is there, coherence is, we have to think about the coherence, how the cache coherence happens. So the problem is when we are working in this heterogeneous environment, so how we are going to achieve the cache coherency. So we have multiple domains with separate caches share the same memory. So we need to ensure that if the shared resources are changed in any cache, that change should visible throughout the entire system. So this cache coherence is a main concept that they are going to talk about in this research paper. So cache coherence is the consistency of data stored in the cache memory. Maintaining cache and memory consistency in is vital for multiprocessors and distributed shared memory systems. So cache management is structured that they have to think that the data is not overwritten or lost. So as a solution, they have come up with this K2. So this K2 is an uh, test. It's a prototype operating system for multi-domain mobile SoCs. So in here, through this research paper, they uh, try to give the answer. They try to find the answer for the whether we can whether we can span an operating system across multiple coherence domains. To show that they have that they can span an operating system across coherence domains, by they come up with this, that they mention that by doing the properly refactoring and the existing OS, that they have identified the shared most OS model where OS services are replicated in all domains under with the transparent state coherence, while a small selective set of services operates independently in each domain. So let's move to the K2 operating system. So this is the background of the SOCs, what is heterogeneous and coherence. So after having that knowledge, we can move to the K2 operating system. First of all, I would like to draw your attention for what are the design goals of this K2 operating system. So this K2 operating system is designed. Uh, the design goals of this one is first to facilitate application development by relieving application developers from dealing with incoherent program state and fragmented system images. And the second one, simplify the OS engineering by avoiding by trying to use the legacy OS code maximum and maintain the current performance level of demanding tasks. So these are the three design goals of designing this K2 operating system. And also we call this as shared most operating system. So after come up with the design goals, they have made some assumptions, architectural assumptions on this K2 operating system. The first one is they are using heterogeneous cores. So this system on chips has multiple types of cores that provide different performance power trade-offs. So these cores may have different instruction set architectures. Right. The second one is the multiple coherence domains. So this multiple coherence domains means all cores on the system on chip are isolated into few 2 to 3 coherence domains for achieve this high heterogeneity. Within the coherence domains, there may be multiple cores 2 to 8 as a traditional multi-core. So there is no hardware cache coherence among these domains. The third one is the shared platform resources. So coherence domains are connected to a chip level interconnect and share all the platform resources including RAM and I/O peripherals. So interrupt generated by I/O peripherals are physically wired to all domains. And then the aggressive power management. These cores are taken online, active and inactive from time to time, which will save the energy of this system. So then we need to think, now we discuss the design goals and the assumptions of architectural assumptions they have made in order to design this K2 operating system. We need to see where this K2 mobile operating system stays in our operating system spectrum. In here, there are, without going to the extremes of shared everything and shared nothing, this shared most, our K2 operating system stays in the middle of the this OS spectrum. In here, in the shared everything, that means for example Linux, Windows, they are using coherent multicores, and then shared nothing like Barrelfish, FOSS, etc., and they use the incoherent many-core structure. So in our K2 mobile operating system, we call it as shared most operating system, which stays in the middle of the those two extremes. So we have this multi-domain mobile system on chips in shared most operating systems. So we have identified that we discussed the design goals. In order to achieve these goals, we identify this shared OS model. So this shared most OS model will have these techniques to achieve those goals. Transparent shared state for extended services. So in this paper, they argue that the OS should transparently maintain state coherence for replicas of extended services, including device drivers and file systems. And the second one is the independent instances of core services. So in here they mention that for a core service, the OS creates independent per domain instances that share no internal state. So in here the core services such as memory management are invoked frequently and are performance critical, and those core services are performance critical. So by replicating such services over multiple domains, so contention must be carefully avoided for performance. And also when they're creating independent instances of core services, this will rise to design problems, how and when the OS should coordinate in independent services, and how to minimize the modifications to the mature implementation of core services. So this way we can meet that design goal, that simplified OS engineering. For these two, if we can achieve these two techniques from our shared MOS model, then we can go to that simplified OS engineering. Uh, it's one design goal of this shared MOS OS model. So how we are going to address these two questions, we are going to discuss in the future slides. So then the third one is avoid multi-domain parallelism within individual process. Here threads belong to the same process, share an extensive set of OS state. Example, open files. So running them um, simultaneously on multiple domains may lead to expensive contention. But the application will get little benefit from that kind of parallelism. But we argue that such contention should be prevented um, by always by differing to light task execution if the same process has more demanding tasks to run. So in here, these three concepts, they are going to build in this shared most OS model. So then let's move to the K2 operating system. Now we discuss the design goals, assumptions, and what is this shared OS model, and where our K2 operating system stays in our OS spectrum. And then we can move on to the hardware platform the K2 operating system uses. So in the hardware platform, so we are using heterogeneous cores in the two coherence domains of OMAP4. Here you can see Cortex A9, a strong one, and Cortex M3 weak domain. So in here, Cortex A9, they are using different instruction set architectures, frequencies, cache, and MMUs, memory management units. Right. So in this OMAP4 has two coherence domains, and each of which host one type of 32-bit ARM core. So the performance oriented, we call this performer A9, Cortex A9 as the performance oriented one, and the efficiency oriented, we have Cortex M3. So all the specifications are given in this table. So OMAP4 has non-standard memory management unit in which this Cortex M3 has that kind of memory management unit, which will connect two levels in series. This will affect the design of K2 software coherence. So we are going to talk about this software coherence in the future future slides. So each domain has dual cores and a private interrupt controller. So both domains are connected to the system interconnect, with which further connects to the shared RAM and all the I/O peripherals. So to support this multiple coherence domains, OMAP4 provides two facilities. The one is the hardware spin locks. We are using these hardware spin locks for interdomain synchronization, and we have set of which there are set of memory mapped bits that support atomic test and set, and then hardware mailboxes for interdomain communication. That cores can pass 32-bit messages across domains with interrupting each other. So this K2 is using this OMAP4 with many platform specific optimizations and workarounds um, with workarounds. So this is the hardware platform that we are going to test in our K2 operating system, and let's see how the operating system structure is developed in this K2 OS. So in here, as you can see, we have the main kernel and a shadow kernel. So there are two kernels in the K2 operating system, and then single system image. We have the system interconnect in the below to these kernels, and we have shadow services inside the main kernel, shadow services, private services, and independent services. And then in the shadow kernel also we have the shadow services, independent services, and some set of private services. So this main kernel is using the ARM Cortex A9, and shadow kernel is using ARM Cortex M3. Right, then from an application developer's perspective, they develop the performance critical parts of their application as normal threads for execution on the strong domain in here in the main kernel, and they wrap their light tasks in special light watch threads which will be pinned on the weak domain, or we call it as the shadowed kernel. So under the single system image, so K2 runs these two kernels on OMAP4 platform. The full-fledged main kernel is an ARM instruction set architecture running, and on the strong Cortex A9 cores, and Lee in the shadow kernel it uses thumb2 instruction set architecture and running on the weak Cortex M3 core. So these kernels share the same virtual address space and the same pool of physical memory. So how they are going to use this virtual space and the physical memory we are going to discuss later. And also most of the operating system services, including device drivers and file systems, are shadowed between both kernels. So they are built from the same source code, and K2 transparently keeps their state coherent at runtime. So there are few core services that are independent to both kernels and K2 kernels, and this K2 will coordinate them on the meta level. So each kernel has its private services as well. So that's all we are going to talk about this K2 uh, operating system structure. Now let's move to the let's see what are the core services that we'll get from this K2 operating system.
In the next section, we are going to describe about the core components of the K2 OS. So first we'll look into memory management. So memory management is the functionality of an OS which handles or manages the primary memory, and memory management keeps track of each and every memory location, either it is allocated to some process or it is free. So it checks how much memory is to be allocated to process, and it decides which process will get the memory at what time. So it tracks whenever some memory gets free or unallocated, and correspondingly it updates the status. So in K2 they will be considering the Linux virtual features and with some additional constraints. So here first they are in the paper they are discussing about the concept they are using in the Linux environment. So the mapping between the virtual address and the physical address is directly mapped. So the mapping is linear and permanent, and any virtual address is mapped to a physical address that only differs by a constant of offset. So such direct mapping, it simplifies the kernel's virtual memory designs. So accessing the direct map memory will never give a page fault, and the conversation between the kernel and the virtual and the physical kernel are fast. So these are the advantages by using the linear mapping, direct mapping. But when they are going to introduce this in the K2 operating system, they have some constraints. So the first one is memory objects shared between kernels must have identical virtual address in both kernels. So in the strong kernel as well as in the weak kernel, they must have a identical virtual address. In addition, private memory objects should reside in non-overlapping address ranges to help catch software bugs. The next one is for each kernel, the assumption of linear mapping holds for the entire direct map memory. And the third one is contiguous physical memory should be maximized, in particular for the main kernel, which usually needs the large physical memory blocks for multimedia application. So K2 arranges its kernel address space according to the figure given now. So this is the unified kernel virtual address space of K2. So here we can see this physical memory consists of two regions. So both are directly mapped with the, so here we can see the virtual address, and on top of that physical memory there are these two regions which consist of two regions, and both two regions are virtual address are directly mapped with the physical address. So the small one is local region, which hosts the executable codes in the memory objects, which allocated for private or independent OS services. So the existing remaining part is allocated for the global region in the physical memory, which belongs to host the memory objects of shared OS services and free the physical pages for dynamic allocation. So according to this figure, we can easily identify this darkly marked part is for the global region and this one is for the local one, and again in the local one we can see the shadow kernel, and this is for the main kernel. From the end of the last local region, the global region spans to end of the physical memory. So by putting the main kernel local region, here we can see before the global region we have local main region. So by putting this one near to the global region, they avoid the memory holes, and here they are using the temporary mapping. In addition to the direct mapped memory discussed now, they having the temporary memory mapping as well. So there are two major types of temporary mapping they are using. So first one is for the accessing the input-output memory. So these creations and destruction of this kind of such mappings are infrequent. So K2 adapt a simple protocol between these two kernels to do these page tables updates from one to another. So the second temporary mapping is on platform with existing memory resources. So the amount of pages can be exceed and then can be directly mapped into to the kernel space. So therefore the temporary mapping is needed on demand when they need for the extra pages. So these are the two ways of they are having the temporary mapping. When we look into the physical memory management, physical memory management is a process is allocated physical memory whenever that memory is available and program needs it. So in our K2 we should require the minimum interdomain communication in memory allocation and free. Since we have two domains, we need to have a minimum communication between these two domains. And in K2OS, it should enable the both kernels to dynamically share the entire pool of free pages and avoid disruptive changes to the existing Linux page allocator, which is already a mature design with sophisticated mechanism and policies, and it should minimize the physical memory fragmentation. So to achieve this require minimum interdomain communication, K2 applies the shared most model and it creates instances of page allocator in both the main kernels and shadow kernels. In both kernels they have separate instances of the page allocator, which has the separated states. They have different states. So the allocation of the request are normally served by the local instance on the same coherence domain, and they have a new concept called balloon drivers. So the balloon driver is a pseudocode device driver, and each kernel has the local kernel as well as the main one. Each has its own private instance, which is controlled by the K2. So the driver's job is to occupy the contiguous physical memory to keep the memory from the local page allocation. So according to this figure, we can see a balloon driver. We can see the balloon driver, and it provides two states. It provides two primitives. Those are deflate and inflate. So the deflate one is shown in the green color arrows and the inflate one is in the red color arrows. So the deflates one, the driver frees a page block to the local page allocator, which is essentially transfers the ownership of the page block from the K2 to the local kernel. And the inflate, the driver allocates a page block from the kernel to the ownership will be of the page block from the local kernel back to the K2. So in the early stage, the kernel boot balloon drivers of both kernels are initialized to occupy the entire shared region, so that K2 owns only all physical pages in the region. Then there's another concept called meta level manager. So on top of the balloon driver, K2 provides a meta level manager. It will decide when to take and give the page blocks from the kernel to the K2 or K2 to the kernel. So it is the one which is going to decide that. So here the meta level manager is implemented is a set of distributed probes. So generally when memory pressure increases and before the local kernel reacts to the pressure, the meta level manager instructs the balloon driver to free the page blocks to elevate the pressure. So when free pages are run low in the entire system, the meta level manager instructs the balloon driver to inflate for the reclaiming the pages. So this is how the meta level manager works. And K2 applies a few optimizations in physical memory management. So the first optimization is to reduce the interdomain communication. The meta level manager operates on large grain page blocks. So the large grain size will be somehow 16 MB in the current implementation. And the second optimization the K2 is using is to maximize the size of the physically contiguous area available to the main kernel. So meta level manager will notify the balloon to deflate from the two ends of the free portion in the shared region, and it will inflate in the reverse direction. So then the third optimization is to maximize the chance of successfully reclaiming the page blocks from the kernels. So K2 commands the local page allocator to place the movable pages to close the frontier of the balloon with the best efforts. So as a result, when the balloons inflates, the movable pages can be evacuated from the requested page block to elsewhere. So next we will look into the software coherence. So K2 provides transparent coherence for shadowed services. So this is implemented with the software distributed shared memory. So like most DSM design, K2 DSM maintains the key one write in invariant. So by automatically translating the memory access to the interdomain communication for coherence. So the basic design is the K2 DSM implements sequential consistency. So in implementing the sequential consistency, the K2 performs the coherence operation upon each access false and keeps order of the coherence messages. So K2 DSM adopts granularity using 4 KB page as the smallest memory unit. So K2 DSM has adopted a simple and standard two-state protocol for this. So for each shared page, every kernel keeps track of its states, whether it is valid or invalid. So kernel communicate between these two types of coherence messages between these two states. So those two messages are get exclusive and put exclusive. So when if we consider the situation, so when a page is valid, then the kernel can perform read or write operations for the valid pages. So before performing that read and write operation, what the kernel will do is it must send get exclusive message to the kernel who is currently on that page. So to the owner of the page, this kernel should send the get exclusive message. So upon receiving the get exclusive, then later kernel flushes and invalidates the requested pages from its local cache, and it will acknowledge with that kernel will acknowledge with the put exclusive message. So after that, then the former kernel can proceed with the memory access. So this is how this design is designed. So when a page transits from valid to invalid states, the DSM modifies the corresponding page table entry, where in the page table they will have with what state of that page is. So the resulting page fault triggered by the subsequent access to the page. So the fault handling is transparent to the OS, K2 OS code, and that made the memory access. When we consider the communication of the coherence, for the performance, the coherent communication directly uses the OMAP for hardware mailboxes. So they carefully construct the coherence communication to avoid the lockup. So the communication must be synchronous to the requester. So this is because interrupt handlers which cannot sleep may access the shared state that initiates the communication. So the optimization of the memory footprint is the K2 DSM has a low overhead in storing protocol information. So although the shared memory areas have to be mapped in granularity, the K2 DSM allows non-shared areas to be mapped in the large grids. So 1 MB or 16 MB as supported according to the ARM hardware. So by reducing the size of the page table and elevating to the TABB pressure, to achieve this, the K2 DSM turns on the software coherence of the memory address, and it will replace the existing mapping on demand only when an address has been accessed by the both kernels. So when the next main concept is interrupt management. So here multiple according to our operating system, multiple coherence domains share interrupt generated by the I/O peripherals. So although any interrupt signal can be physically damaged delivered to the old domain, so we must make sure that is every interrupt is handled by exactly one kernel. So if multiple kernels are competing going to the same interrupt signal, then it may enter incorrect state. So we need to make sure that interrupt is handled by only exactly one kernel. So the choice of the kernel in handling the interrupts does not affect the OS correctness. So K2 coordinates its two kernels in handling shared interrupts by following two simple rules. So the first rule is energy efficiency. For the energy efficiency, K2 will not allow shared interrupts to wake up the strong domain from an inactive power state. So when a strong domain is going to come to the active states, then the energy will lose a lot. So in order to make the energy efficiency, it will not allow the shared interrupts to wake up the strong domain from an inactive power state. In that case, the shadow kernel should handle the interrupt. So in the second one is they are considering about the performance. So when the strong domain is awake, then K2 will let the main kernel to handle all the shared interrupts. So it avoids the main kernel from the inactive state to handle these interrupts. Then we'll look into the night watch threads. So as we mentioned before, K2 provides an abstraction called night watch thread, which is for the light task. So the night watch threads will be main. After being created, a night watch thread enters to the shadow kernel queue. So the only exception is that so normally we can say that night watch thread can be like a normal thread. So but only the exception here is in order to limit the multi-domain parallelism, K2 enforces that a night watch thread will only be considered for scheduling when all normal threads of the same processors are suspended. So here if we consider when it is going to preempt and when it is going to resume the night watch threads, so K2 preempts the execution of all Nightwatch threads in a process when the normal threads of the same process is about to execute, and after the main kernel decide to schedule in a normal thread, it examines if any Nightwatch threads are belong to the same processes are running. It will check whether there are any Nightwatch threads for the same process is running before it handles it gives the handling to the normal thread. So if there is anything Nightwatch thread is running, then it will the kernel will send the suspend NW hardware message to the shadow kernel. So the interrupted by the suspend message, the shadow kernel immediately responds with an ACK suspend message and then removes all Nightwatch threads for the same process. So by you sending these suspend and ACK suspend messages, both kernels will check whether the Nightwatch threads are running. So if we consider when it will resume the Nightwatch threads, so the main kernel finds that all the normal threads of a processes are blocked. Say for an example, it can be blocked for an input-output operation. So when it finds that all the Nightwatch threads are blocked for some reasons, then it will send a resume message to the shadow kernel. So when the shadow kernel receives that message, so it removes the flags from the old Nightwatch threads and it will give the process to the Nightwatch threads. So this is how the Nightwatch threads are working. So let's move to the evaluation. So the K2 introduce, so it's a variation. It has some more features than the Linux, where the K2 introduces the small changes to the Linux source. So the biggest portion of the biggest change is done in the exception handling, where it handles the page faults for the DSM operations and dispatches the function pointers. So to core OS components such as page allocators. So K2 only has a small portion of source lines. So when we are going to evaluate these both kernels, so we are going to consider the three benchmarks. In this research paper, they have considered the three benchmarks. The first one is the DMA driver, and then the ext2 file system, and then the UDP log, then the UDP loopback. So the first one is DMA driver. So here they choose the DMA driver as a representative device driver for testing, so which is almost used for the bulk IO operations. So the driver executes the DMA transfers when the DMA OMP for DMA engine starts the operation. So according to this figure, they have picked a set of DMA transfer sizes. We can see there are a set of sizes in the x-axis. So they have chosen set of sizes to light tasks. So each run of the benchmark repeatedly invokes the DMA driver and it will execute multiple memory to memory transfers. So they are going to calculate the batch size and the total size. So when the transfer is done, the DMA driver is interrupted to free the resources. It will free the resources and it will complete the transfer. So then they calculate the energy efficiency as the amount of transferred bytes per joule. Then their next benchmark is ext2 file system. So they choose that file system widely used for flash storage to test the energy efficiency of the file system workload. So they use the run disk as the underlying block device, and according to this picture we can see for each run a Nightwatch thread operates on 8 files sequentially. So it creates a file, writes to it, and then it closes it. So they vary the write size to represent the different content times. There we can see the write sizes 1 KB, 256 KB and 1224 KB. So they calculate the energy efficiency as the number of bytes written per joule. Then the next benchmark is UDP loopback. To test the network workload efficiency, they design a UDP loopback benchmark for the network. activities when the light has fetch the contents from the cloud. So to evaluate that one, they are going to use this UDP look back. So there in the picture also, in the last part we can see they have chosen the sizes to represent the typical context as done for the EX2 benchmark. So they calculate the energy efficiency as the amount of bytes cents per joule. So as a result, this shows that it has significant energy advantages of energy efficiency over the Linux. So the energy efficiency is more considered in the K2 operating system.